The quantum electrodynamic vacuum, or QED vacuum, is the field-theoretic vacuum of quantum electrodynamics. It is the lowest energy state of the electromagnetic field when the fields are quantized. When Planck's constant is hypothetically allowed to approach zero, QED vacuum is converted to classical vacuum, which is to say, the vacuum of classical electromagnetism. Another field-theoretic vacuum is the QCD vacuum of the Standard Model. Fluctuations. The QED vacuum is subject to fluctuations about a dormant zero average field condition. Here is a description of the quantum vacuum. The quantum theory asserts that a vacuum, even the most perfect vacuum devoid of any matter, is not really empty. Rather, the quantum vacuum can be depicted as a sea of continuously appearing and disappearing pairs of particles that manifest themselves in the apparent jostling of particles that is quite distinct from their thermal motions. These particles are virtual, as opposed to real particles. At any given instant, the vacuum is full of such virtual pairs, which leave their signature behind. By affecting the energy levels of atoms, Joseph Silk on the shores of the unknown 62 virtual particles, it is sometimes attempted to provide an intuitive picture of virtual particles based upon the Heisenberg energy-time uncertainty principle, arguing along the lines that the short lifetime of virtual particles allows the borrowing of large energies from the vacuum and thus permits particle generation for short times. This interpretation of the energy-time uncertainty relation is not universally accepted. However, one issue is the use of an uncertainty relation limiting measurement accuracy, as though a time uncertainty delta T determines a budget for borrowing energy delta E. Another issue is the meaning of time in this relation, because energy and time do not satisfy a canonical commutation relation. Various schemes have been advanced to construct an observable that has some kind of time interpretation, and yet does satisfy a canonical commutation relation with energy. The many approaches to the energy-time uncertainty principle are a continuing subject of study. Quantization of the fields. The Heisenberg uncertainty principle does not allow a particle to exist in a state in which the particle is simultaneously at a fixed location, say the origin of coordinates, and has also zero momentum. Instead, the particle has a range of momentum in spread in location attributable to quantum fluctuations. If confined, it has a zero-point energy. An uncertainty principle applies to all quantum mechanical operators that do not commute. In particular, it applies also to the electromagnetic field. A digression follows to flesh out the role of commutators for the electromagnetic field. Because of the non-commutation of field variables, the variances of the fields cannot be zero, although their averages are zero. The electromagnetic field has therefore a zero-point energy, and a lowest quantum state. The interaction of an excited atom with this lowest quantum state of the electromagnetic field is what leads to spontaneous emission. The transition of an excited atom to a state of lower energy by emission of a photon even when no external perturbation of the atom is present. Electromagnetic properties. As a result of quantization, the quantum electrodynamic vacuum can be considered as a material medium. It is capable of vacuum polarization. In particular, the force law between charged particles is affected. The electrical permittivity of quantum electrodynamic vacuum can be calculated, and it differs slightly from the simple epsilon zero of the classical vacuum. Likewise, its permeability can be calculated and differs slightly from mu zero. This medium is a dielectric with relative dielectric constant greater than 1, and is diamagnetic, with relative magnetic permeability less than 1. Under some extreme circumstances in which the field exceeds the Schwinger limit, the quantum electrodynamic vacuum is thought to exhibit nonlinearity in the fields. Calculations also indicate birefringence and diquism at high fields. Many of electromagnetic effects of the vacuum are small, and only recently have experiments been designed to enable the observation of nonlinear effects. PVLAS and other teams are working towards the needed sensitivity to detect QED effects. Attainability. A perfect vacuum is itself only attainable in principle. It is an idealization, like absolute zero for temperature, that can be approached, but never actually realized. Virtual particles make a perfect vacuum unrealizable, but leave open the question of attainability of a quantum electrodynamic vacuum or QED vacuum. Predictions of QED vacuums such as spontaneous emission, the Casimir effect and the Lamb shift have been experimentally verified, suggesting QED vacuum is a good model for a high-quality realizable vacuum. There are competing theoretical models for vacuum, however. For example, quantum chromodynamic vacuum includes many virtual particles not treated in quantum electrodynamics. The vacuum of quantum gravity treats gravitational effects not included in the standard model. It remains an open question whether further refinements in experimental technique ultimately will support another model for realizable vacuum.